Hi, and welcome to our 1 p.m. press conference, The Growing Great Pacific Garbage Patch. Our speaker this afternoon is Charles Moore from Algalita in Long Beach, California.
Hi, good afternoon. Enjoying my stay here in Portland and beautiful sunny Portland. I think I'm back in Los Angeles where I'm from. I don't know if it's usual, but it's certainly welcome. And my topic is the accumulation of the detritus of civilization in accumulation zones in the ocean. Our civilization has expanded via the lubricant of globalization, which is plastic. Plastic affords products the ability to be shipped around the world and arrive in a pristine condition. It's really facilitated global trade. I call it infinite trade. Trade everywhere of everything is facilitated by plastic. Our problem is that this material doesn't biodegrade, and at the same time, it accumulates. Ocean is downhill from everywhere. We have no take-back infrastructure for this stuff, and it's becoming a major problem in the ocean. So I began Algalita Marine Research Foundation in 1994 to look at issues around marine algae, around the disappearance of Macrocystis pyrifera, the giant kelp in Southern California, as kind of a climate issue. The giant kelp is the rainforest of the ocean. But in 1997, I crossed through the Great Pacific Garbage Patch. It had not been named at that time, and was astounded to see plastic in the middle of nowhere, basically as far from human civilization as you can get anywhere on the planet. So the group that I founded shifted its focus and now works entirely on the issue of plastic pollution. So I'm going to give you an introduction to that group and then talk a little bit about my presentation here at the Ocean Sciences Conference.
Studies one of the most serious threats to our planet, ocean plastic pollution. Since 1999, we've worked to understand the complexities of this issue. Our work in the North Pacific Gyre has ignited a global movement to prevent ocean plastic pollution worldwide. Effective environmental education by bridging real-world science with real-time solutions. We're committed to preparing the next generation to deal with the challenges ahead.
So now that you've seen an issue that is growing in scope, our question for the conference here today was just how much has that grown? Has the amount of plastic in the North Pacific Gyre changed? But there's a lot of factors that complicate that answer. So that's what we explored in our presentation here at the conference. Let me go ahead and maximize that so you can see it. Okay, so one thing is not disputed, and that is that global plastic input to the ocean continues to grow. It's growing really fast, and it's huge. Jambeck et al. Estimated that between 4 and 12 tons of million tons of plastic enter the ocean each year. The figure you hear thrown around is the average 8 million tons entering the ocean every year. That's a tremendous amount of trash to be entering the ocean. Now, people have looked at this area, this Great Pacific Garbage Patch, in a number of ways, a number of different studies using a number of different types of equipment, and their conclusions have varied widely. So many factors affect this issue. Our goal here was to present a 15-year time series. We've been going to the same place for 15 years and look at the variability due to ocean dynamics and submergence of the plastic by winds. These 11 transects were sampled 5 times over 4 sampling years, and then these core sites were supplemented with 316 other sites over the 10 years that, actually 15 years that we've been doing this work. This is the international date line right here. This is where the farthest west we've gone. This is Hawaii down here, and this is San Francisco right here. So this garbage patch is in this area right here, but it's not static. It's not a static place. However, we do monitor a static geographic location, this kind of inverted V right here. Half of the stations are east-west and half north-south. That we've gone back to and monitored over and over again. And we've seen a tremendous increase there. We've seen it go, and that's the reason for why in our abstract you see such high numbers as a 60-fold increase, because different ways of looking at it show extreme increases in the amount of plastic there. However, the gyre is not a static place, and what our hypothesis was here at the conference was that as the amount of Newston plastic is sampled, it depends on how far it is from this moving center of the garbage patch. And we used a model done by Maximenko and Hafner out of the University of Hawaii. And their model shows this thing moving around. You can see here, in 1999, we happened to be that first sampling cruise that actually found 6 times as much plastic as plankton was not even near the center. And this thing wobbles. Now here in 2014, it's much closer to the coast. In order to get out to our sampling area from the Long Beach, Los Angeles area, we had to pass through the center of it. So we actually saw a lot more plastic on the way out there this time than we had ever seen before. But it was because this center had moved right over here, much closer to the coast. It can move 1,000 kilometers from one position to the next. And if you look at our samples, you see that as you are closer, you get the higher amounts. It's really clear that the distance from the gyre center matters. So I'm going to skip down now to our conclusion, because we found out that wind wasn't that big of a deal. So if you look at with the wind factored in over all of our stations, you see it's gone up 5 times in the garbage patch, but if you look at it without the wind, it's gone up 14 times. So it's not 60 times, but it's certainly a large amount. It certainly is increasing, and we're seeing a lot of effects from that. So one way of looking at it, going to a static location is not the right way to determine trends, even though we see an enormous trend, and I experienced it. I saw it. I knew we would see a heck of a lot more than we'd ever seen before. I'm the eyes on the ground. I'm sort of the ambassador of the gyres. There's very few people, if any, that have gone as many times as I have to the gyre and looked at it and been there. And I saw this increase. But I didn't know that I was, at that time, much closer to the center than I'd ever been before. So that kind of thing has to be taken into account. Now, we also went to the South Pacific gyre this last year and looked at the garbage patch there. So I want you to be able to see a little bit about that before we wind this up, because it's also quite interesting to know about what's happening in the South Pacific
The
garbage
South
patch.
Pacific Ocean. A vast marine landscape, a precious part of our Earth. But take a closer look, and scientists say it's becoming a plastic garbage dump.
Here I am standing on High Zex Buoy Island.
Meet Captain Charles Moore, founder of Algalita Marine Research and Education, a non-profit group dedicated to solving the sea's plastic pollution problem. In 1997, Captain Moore discovered a massive garbage patch in the North Pacific. Now his team has confirmed the existence of another further south off the coast of Chile and Peru. Captain Moore estimates it to be about 2 million square kilometers, larger than Mexico. Here's how it formed. Winds around a persistent high-pressure system drive ocean currents, creating a vortex known as a gyre, causing debris to collect in a central location.
I call it a plastic soup. If you think of the ocean as the liquid in a soup, we've gone from, creamy to extra chunky.
Captain Moore and his team spent months trawling the South Pacific collecting samples from large objects to plastic the size of a grain of rice.
The surface waters are where we see the debris, and it is mostly particulate. The size class that's most common is between 1 and 3 millimeters in diameter. But we find interesting objects. A lot of tubs that are used in sorting fish in the fisheries that are manufactured in New Zealand. We found a lot of fishing buoys, and of course, the most common things that we find out there are the floating bottles and the bottle caps.
The plastic poses a major threat to marine life. Small lanternfish come to the surface at night to feed on plankton. Many eat small microplastics instead and are then unable to swim back to the bottom, the plastic acting like a buoy. Not only do these fish ingest chemicals from the plastic, but so do the larger fish who eat them. Algalita Marine Research found 35% of lanternfish in the previously discovered North Pacific garbage patch are eating plastic. The researchers are now sifting through the samples to try to get a better understanding of what types of plastic they've collected. But Captain Moore says it's our throwaway society that needs to change.
We have to fear plastic for not only what it does to the marine environment, but what it's doing to us. We need to fear it, and we need to respect it because it is being treated like waste, like trash, like it's just this wrapper that you throw away. And we've got to have a new attitude about that in which we realize that it must have an afterlife. It must be reincarnated. It must be part of a circular economy, or it's going to end up in the ocean and destroy marine life. So we are now working with plastic companies, with Coca-Cola, with U.S.A. We're working desperately to reshape the thinking of those who are making this stuff, to create this infrastructure, to take it back, to have a circular economy.
Linda Kincaid, CNN.
So we actually are starting a chapter of Algalita now in the South Pacific. That bin that you saw there from New Zealand that is used to sort fish so shocked my first mate, who is a New Zealand native, because that company has a green reputation in New Zealand that they really tout about the fish that they harvest. And the fact that they're losing their plastic into the ocean is not a good thing. So she's taking our message to New Zealand and starting a new chapter of Algalita South Pacific in New Zealand, and we'll be branching out to Chile, where we studied along the coast of Chile. Now, those lanternfish are very important with relation to climate change because they sequester an enormous amount of carbon. You may not know this, but you take that genus of fish, the lanternfish, and it weighs more than all the other fish in the ocean put together. It's over 50% of fish biomass. And it's doing this deal migration every day. It's going up to the surface, eating, and going back down. If we're preventing it from sequestering that carbon, it's adding to the climate that the ability of the ocean to sequester carbon is being defeated by our plastic. And there's many other aspects of plastic that may have a role in that, but this, I think, may be one of the most serious ones. And I'd like to acknowledge my co-author, Cassandra Phillips. We wrote the book Plastic Ocean, which is about the discovery of the garbage patch. And I think it's important that we continue this discussion, but We've only talked now about issues affecting plastics in wild-caught fisheries. You saw the ghost nets there. But what we actually have is we have a situation in which half of our seafood now is produced by farming. We've depleted the ocean of wild stocks, and we're farming our fish. Now, they also have a tremendous role in this problem, and I'd like to end on that note. These are the most common buoy I find out in the garbage patch, but here I discovered this in an NHK special on plastic pollution and asked them to give me the footage. This is a sea urchin farm in Korea, and those buoys, those glass buoys are the most common glass buoy we find out there, and the black plastic buoys are the most common buoy we find out in the garbage patch. And now I know where they come from. They come from aquaculture. These, you'll see them pulling up sea urchins out of this net. So aquaculture has standards for being sustainable, and nowhere in those standards do they mention loss of gear. It's all about, you know, the benthos and whether or not they're affecting it with their food and so on. They really need to mark and monitor their loss. Look at the scale of oyster farming in China, the enormous scale of oyster farming in China. This is unprotected styrofoam, completely degrading into the environment. You'll see exactly how that happens. These oysters are full of plastic. All the research shows that every one of those oysters has plastic in it. We're consuming plastic along with our seafood. More and more we're seeing that. And just look how these buoys decay. It's absolutely astounding that that would be the method on which we're going to feed humanity, because we'll destroy the natural environment using that method. If you pick up a handful of seagrass on this beach, it's half styrofoam. Now, we're going to do a little repetition here, but I want you to see underneath this island that I discovered what's going on. So I'm playing this for you too.
Hyzex Buoy Island. These Hyzex buoys, these large black buoys, were released by the Japanese tsunami on March 11th, 2011, and came as part of an array that was used in oyster aquaculture. Each buoy has a rope on it with scallop shells woven into the rope for oyster spat to recruit to and grow on. This oyster farming operation was wrecked, including the anchoring structure, and drifted out here into the Central Pacific, forming an island. Well, this is an interesting sample, as we have oyster spacers from the oyster aquaculture industry.
Those
We
are
have
very
two
common
oyster
in our
spacers
trawls.
in here.
And what we're going to see now is what's called ghost fishing. The fact that this is out there, it's collecting other kinds of nets. And some of those nets are used in coastal fisheries that are the real hard to see, clear monofilament. And I don't think there's any better example of ghost fishing than what you're seeing right here. That's a true ghost. That is a fish like these pelagic chub that are swimming around there that was caught there. Maybe it was at night, maybe it didn't see it, maybe it was just swimming around, it got caught, it struggled, it tried to get through there, couldn't make it, died, was decomposed by bacteria, but at the same time it left this white skeleton. Truly a ghost. Ghost fishing is going on. Millions of fish are dying because of it. It's an incredible situation that is only getting worse. And just to bring it home, this is Puget Sound. 40,000 of these PVC tubes are used in every acre of geoduck clam aquaculture in Puget Sound. They're being lost to the Sound. Trawls in the Sound find hundreds of them. And they're the toxic plastic. PVC plastic leaches a lot of toxicants into the marine environment. So if you had some mussels over here at the Eastland Hotel, they're famous for their Thai mussels with curry. Those were grown up here in Puget Sound, and that operation is releasing a lot of plastics into the environment. I've served as an expert witness for groups attempting to slow down the proliferation of aquaculture operations in the intertidal zone and in the Sound itself. So I'd like to stop there and thank you for your attention and offer the floor to anyone who'd like to ask some questions.
Great. We'll now open it up to any reporters in the room who have questions. Please raise your hand and state your name and affiliation. Are there any other?
Rick Lovett, freelance. I'll start us off. So we had a previous session where we were talking about microplastics. And I'm not quite sure what size you're trawling for. That number went through fairly quickly. But do these become, I mean, what is the fate of this stuff out there? Does it degrade into microplastics?
Yeah, the process is one of continuous formation of nanoplastics from macroplastics. The macro class, we normally go 5 millimeters and above. We call the macro class. Between that and 3, 5, 5, about a third of a millimeter, that's what the mesh of most of these surface trawls are, a third of a millimeter mesh net. So that's the stuff we're pulling up in our nets. But many of those particles are smaller than a third of a millimeter. Those third of a millimeter particles are escaping our net. They're becoming nanoplastics. Nanoplastics have the property of acting like the seawater itself. They're not buoyant anymore. They have so much drag, the water appears as super viscous to a tiny little particle, so it actually becomes part of the water column. So what happens is that any breaking waves, any movement of current, any macro current system, any large or even small mesoscale current system can take these nanoplastics with it. It just becomes part of the ocean itself. So they're distributed entirely throughout the water column from the benthos all the way to the surface. Actually, a little over 50% of all plastics coming out of the manufacturing plant are heavier than seawater. So your clothing fibers will sink to the bottom pretty quickly. They're Dacron polyester, PET, polyethylene terephthalate is a synonym for Dacron polyester. Dacron polyester is what we wear in our fleece, what much of our clothes is made out of, what Patagonia uses. Those are fibers that are heavier than seawater. Those are the fibers that we're finding. Nevertheless, just because they're heavier than seawater doesn't mean that they're not in the air. A study in Paris found between 3 and 10 tons of those fibers settling out of the air in a single year. So we're not only ingesting these fibers, we're also breathing these fibers. We're ingesting them with our seafood, we're breathing them in our respiration, and the ocean is absorbing them at the end of the day. So we have this situation where we have a non-biodegradable component of the biosphere that is capable of transporting pollutants. It's very lipophilic. It loves oily contaminants. Much of our pesticides, much of our herbicides, many of the contaminants that we're concerned with, what we call persistent organic pollutants, are carried by plastics. So this vector for carrying pollutants is now ubiquitous, truly ubiquitous in the biosphere, and it's increasing. The projections for the future are plastic production will triple by 2050, and that's when it's predicted to be half plastic, half fish in the ocean. Now, that is based on how many fish are in the ocean now, but we're continuing to extract more and more fish. We're making more and more fish sick. We're catching more and more fish in ghost nets. So the numbers of fish are much likely to be less, and the weight of fish biomass is likely to be a lot less in 2050 than it is now. So this estimate of half plastic, half fish by 2050 may be optimistic.
Are there other questions?
Hi, Carolyn Groundling, Science News. I wanted to ask, in your talk this morning and what you went through here, you mentioned obviously that wind was not a primary controlling factor in terms of the distribution of these plastics. Obviously, distance from
By
the center.
weight, by
By
weight.
weight,
Yeah.
right. Obviously, distance from the center was, what are some of the other factors that do need to be considered when people are modeling how these things are distributed?
Yeah, what we learned today in our seminar was that sunlight is actually an enormous factor. Photodegradation is a very big part of the equation. What photodegradation means is that these polymers, if I could stand up, they are composed of chains, and the chains rest on top of one another, and they slide back and forth. Now, cross-linking is when the UV radiation breaks the chain, and when the UV radiation breaks the chain, it lets part of the polymer go down and stick. Like, I don't know if you remember vinyl tops on cars, but vinyl tops on cars started to crack, and they crack because that thing that no longer slides, it becomes rigid. It's not soft anymore. And that process is occasioned by sunlight. So sunlight is a major factor in the degradation and the removal of plastics. They call it removal. It's not truly removal. It's just relocating the plastics in the environment. Plastics are constantly being relocated by natural forces. We know there's a dictum in ecosystems, everything is used, but nature hasn't figured out how to use plastics. It's still working on it. Lignin, which is the first natural polymer, it took 10 million years in the fossil record for bacteria to evolve to digest lignin. Now we've got all these synthetic polymers of infinite variety, all these different polymers, and there's no bacterial organism that's going to be able to handle that for many, many eons. So the idea that somehow nature will figure out what to do with all this plastic is only a physical movement from one place to another. It's not truly making it part of the natural cycle.
Are there any other questions? Yes.
I'd like to follow up on that because I walked in right at the end of the presentation about UV degradation, and or at least if there's only one. And he was talking about export to the depths. What exactly? So what exactly is the byproduct of this at its, once it's broken down as far as it's known to go? And is that stuff toxic, or does it just going to wind up as a layer of sediment somewhere?
Well, let's start with the last part first. Just a layer of sediment. Do you know what the property of plastic is? It's a vapor barrier and a moisture barrier. So if you coat the bottom of the ocean with plastic, the way we sequester carbon is we sequester it in the pore waters of the sediments. The stuff goes down as marine snow and gets into the bottom sediments. If we blanket the bottom of the ocean with a layer that is not permeable, then we've got a situation in which there's no sequestration of carbon in the pore waters of the sediments. This was brought up by Goldberg 30 years ago, that there's a danger of having plastic cover the ocean bottom and not sequestering carbon. So that was brought up before. Now to get back to the other part about how it moves and whether it's toxic or not, there's a lot of toxics in the ocean, and zooplankton consume them. The sea surface microlayer has a lot of effluent from coal-fired power plants in it, and my colleagues like Chelsea Rockman believe that that's probably a bigger vector for contaminating seafood with pollutants than the plastics is. Plastic is one component of it. It is not healthy to eat. It has no nutritive value. It is a mechanism for transferring contaminants to the benthos. The benthos has over 90% of what's ocean biomass in it. So the benthos is where the life is in the ocean. We certainly don't want to contaminate that, but chances are that the surface plastics are more contaminated than the ones at the very bottom, and that as far as contaminating the food web, we may be doing that better just by feeding the zooplankton than by feeding plastic to the creatures.
Think of another question?
I'm Virginia Guin, I'm freelance. Curious about the companies that you mentioned, Coke and Dow. What exactly are they motivated to do in this space?
They want to burn it. We're part of a group called the Clean, I forget the acronym, but it's Trash Free Seas Alliance, okay? And the Trash Free Seas Alliance was organized by the Ocean Conservancy. We're a founding member of that at Algalita. And it's funded by Ocean Conservancy and the big corporations. And in meetings with them about this issue, they want to put a lot of money into infrastructure in Asia. They basically trash trucks for China, take it to the incinerator. This is their concept. But they found out, hey, China's not really open to us going over there and telling them what to do. So they're thinking now more about Indonesia and Malaysia for their projects. But the basic concept is that Jambeck identified Southeast Asia and China as the biggest contributors, simply not because they were always the biggest contributors, but because the United States and Europe have been displaced by them because of their rapid economic growth. As I said, it's the lubricant of globalization. That's what plastic is. So they're using a lot of throwaway plastics, and the Ocean Conservancy sees this as a crisis. I give them that. The Ocean Conservancy does see this as a crisis. Their response to the crisis is, there's nothing we can do except take it to the incinerator. I've worked more with the zero waste movement. I'm more about no burn, no bury. Everything is a resource waiting to be recovered. We want to see, as I mentioned in the video, we want to see plastic not only feared, but respected. I mean, it took a lot of energy to make this stuff. If you burn it, you're wasting the energy that was put into it to make it in the first place. It's about 8% of the oil barrel is plastic. You know, we're using about 5% of that as the actual polymer, and about 3% is the energy used to make the objects out of the polymer. Now, you're wasting that when you burn it. You're wasting it unless you recycle it. So we think recycling is a higher, or reuse is a higher and better form, but there's no take-back infrastructure. Industry won't provide the take-back infrastructure because they thrive on the throwaway plastic. So we have this huge contradiction, the contradiction between economic drivers, which make for throwaway plastics, and recycling initiatives, which want to recover the plastic. I'm very pessimistic about the future, because what we have ahead of us is a world in which innovation in throwaway is rewarded and innovation in recycling is pushed to the wayside, so that these companies look for exciting new markets. Basically, it's the cute package, the novel package that makes the sale, and that package is not being recycled.
Are there any other questions from reporters in the room? Are there any questions on the chat? No? Okay, great. That concludes our press conference. Thank you very much.
All right, thank you.
All right, great. That concludes our press conferences for today. We will see you back here again tomorrow morning at 9:30 for New Technologies to Observe the Ocean.